Okay, so good afternoon. Today we'll start a new topic. So I guess the new topic is demand paging. I have to update the website. So I noticed that according to the schedule, we should have started this topic last week, but well, that was a tentative schedule. Okay, so let me set up this. And close this guy. Okay, so let's get started. If 99% of the class does the course evaluation, can we final grade without quiz grade? Oh gosh, I wish. I'm telling you, at this point I'm in um, just thinking about designing a final and then grading it is painful. So nobody wants to get rid of the final more than I do, but at this point we can't. To change any kind of grading percentage, I need to get everybody's agreement. So yeah, I feel your pain. When I was a student, I hated finals, and now as a professor, I hate it even more because grading it is nightmare. Okay, so let's talk about the demand paging stuff. Okay, so we're going to talk about demand paging. We're going to see what it is, how it's done, and then look at some approximate algorithms to implement it. These are the two, so the clock algorithm and the nth chance algorithm. Okay, so what is demand paging? Can the final be all multiple choice? Oh God. Let's put it this way. The final will be as fair as the quizzes have been. And I assume that everybody accepts the fact that the quizzes have been fair. I mean, that's the feedback I've got. So I'm not going to, try to trick you with questions. So the questions are going to be straightforward. Close to what you've seen in the quizzes. They might not just be multiple choices, but or true or false, but it will definitely have true or false questions and multiple choices. But it has to also have some, because this is an operating system design and implementation, so it has to have some elements of that as well. Okay, so let's stop talking about the final and get into demand paging. Okay, so what is demand paging? Very high level, demand paging means sharing or multiplexing the physical memory between processes. That's basically high level what demand paging is. Now, we got to know at this point, hopefully, that the virtual address space is huge, and each process has a huge virtual address space. So this everybody should know at this point. In the previous version of Linux, before meltdown attack, your virtual address space was 128 terabyte. Now, we know that, so that's one fact. The second fact is processes barely use their virtual address space. So, in special cases, you might have a process that uses gigabytes of memory. Usually processes use small portions of their virtual address space. And if you focus on a short period of time, it's even smaller. So maybe in one application in its entire lifespan uses some number of gigabytes of memory, but at any given short period of time, it's probably using a very small fraction of that address space. So that's the second fact. Now, the third fact is physical memory is limited. So we don't have a lot of physical memory. So, you know, if you have your laptop, for example, it's probably 8 GB of RAM. If you are talking about data center servers, they have, I don't know, 32 GB, 64 GB, 128 GB of RAM. But 128 GB of RAM is an order of magnitude smaller than the virtual address space of a single process, which is 128 TB. Now, if you're not going to run a single process in your system, you're going to be running multiple processes. In one of the slides, if you remember, I took a snapshot of my own system, my own laptop. There were more than 400 processes running. Okay, so let's put all these facts together. This means that there might be times where the physical memory cannot fit in or cannot contain all the demand from the processes. So maybe processes are asking for more memory than the physical memory can provide. So what should we do at that point? That's where demand paging comes in. Demand paging says, I am going to use memory. I'm going to use my physical memory as a cache for my permanent storage. What does that mean? Well, that means that I'm going to evict a page from one process to make a space for a page for another process. In extreme cases, I might actually swap an entire process out of memory. I might say this process is going to be swapped. If you remember, if you go back to the slides we had when we were talking about processes, we talked about swapping a process out of physical memory. So here it is. If you get into a very strict situation where you really don't have any memory left, and you keep doing this demand paging, you keep evicting one page and bringing another page. At that point, operating system might decide to just shut down 1 or 2 or 3 processes to make a space for the rest of them, so that the rest of them can finish, and then we can bring back the processes that we have shut down. And by shutting down, I mean swapping temporarily to permanent storage. Now, this is high level. So now let's talk about. So in today's lecture, we're going to talk about all the nitty-gritty of demand paging. Okay, so demand paging is basically caching. So we're not going to see much new stuff. So everything that we talked about previously about caches is going to be applied here as well, because we're using memory as a cache for permanent storage. So we're going to look at the same topics that we saw in caching. The first is what is the granularity of caching. When we were talking about caches in multiprocessors or in our processors, we came across this notion of blocks, which was a sequence of bytes that we're going to treat as a unit of caching. So now, what is a unit of caching for demand paging? The unit of caching for demand paging is just pages. So our one page is a unit of caching. We bring in a page, we evict a page. So we're working with pages. What is the organization of the cache? What kind of associativity do we have? If you remember, again, we had direct map cache, fully associative cache, and X-way set associative cache. With memory, we're going to pick fully associative caching, meaning that every page could be anywhere in the memory. So basically, the entire memory is one set. The entire physical memory is one set, and it has as many physical pages as you can fit in, depending on the size of your memory and depending on the size of each page. So that's how many blocks there are. And now each page that we bring, it could be anywhere in the memory. Now, how do we find our pages in caches? If you remember, with caches in processors, we had this tag, and we would check the address with the tag. So what is the equivalent of that here? Well, we have our page tables. So page table tells us where to find each page given the virtual address. And we also saw the TLB, which we can use to find the address translation of our virtual pages. So once you have the address, once you have the physical page number for your page, you can just go there and find it. What is the page replacement policy? If you remember, this is the one thing that I said we're going to just talk about it when we talk about demand paging. Here it comes. In caches, in processors, for eviction, we could have evicted randomly. We could have evicted based on some algorithm. Now, what is the replacement policy here? So let's say we want to bring a page back from a permanent storage to memory. So which page should we evict out? Well, we're going to talk about different algorithms on this. We will, a portion of today's lecture is going to be on those different algorithms that we can apply to pick a candidate to be evicted or a victim to be evicted. What happens on a miss? So if you go to your physical memory and you don't find your page in physical memory, what should happen? Well, you have to go and bring it back from the disk. So you're going to have a missing memory. This means that you're going to go to your disk and bring that page. And this is very expensive, by the way. So we'll talk about that as well. What happens if we write? So if you remember with caches, we talked about two policies, write back and write through. So write back meant that we're going to just write in the cache. And once the cache block is evicted, we're going to go and write it in the memory. Now in this, and then write through was when you write both in cache and memory. Now that memory has become our cache, which one are we going to choose? Well, write through is very expensive because it means that you have to go and write in our permanent storage as well. We're not going to do that, so we have a write back. So we're going to write in memory as many times as the program wants, and eventually once the page wants to be evicted, we're going to write everything back to permanent storage. Now, it's kind of like a deja vu. Many of the things that I kind of kept postponing are coming back. So this is your page table entry for any virtual to physical address translation. Now we're going to work with these bits, the valid bit, the access bit, and the dirty bit. So we're going to use these for demand paging. So I think somebody asked a question on Piazza on examples where this valid bit would come handy. So here it comes. We're going to talk about it. So these are the three bits that in today's lecture we're going to visit and talk about. So the valid bit, we're going to use it to know if the page that we're looking for resides in memory or not. So if the page, if the physical page in memory is for this virtual page, then the translation is valid. It means that I have my page in physical memory. Now, if at any point this page is evicted from physical memory and goes and is written in permanent storage, then I'm going to make the valid bit to 0, indicating that this translation is no longer valid, right? So let's say in the before the eviction, I was mapping virtual page number 2 to physical page number 3. So if I look at my memory, my physical memory, this page number 3 is for this virtual page number 2, right? This is here. Now, the valid bit is 1. It means that this translation is valid. If you get this virtual address and you look at this physical address, this is actually your page. It's valid. Now, let's say I evict this page to permanent storage, and I give this page to someone else. Now, I don't need to change anything here in my page table entry. I only need to make this 0. Now I indicate that, although there is a translation here, there is a translation that says this virtual page is mapped to this physical page, but this is no longer valid because this page number 3 has been evicted for you and now it's been given to someone else. So this translation is no longer valid. So I just invalidated this translation. That's all I need to do. Now, next time, if let's say now this page has gone to memory and later on I want to bring it back, I might bring it back somewhere else. I might bring it back to some page number 10, right? Because I'm going to search my memory and find some space and bring it there. So at that point, when this happens, I'm going to come and update my page table entry, make this guy 10, and make this guy valid again. So now I just changed my translation. Now I'm saying this virtual page is mapped to page table number 10, and now again this translation is valid. So that's the idea. Now, what happens if a reference to a page finds a page table entry that is invalid? Well, at that point, we have a page fault exception. So the hardware that does the page table walk, if it figures out that the valid bit is 0, and this is not a valid translation, it wakes up the kernel and says, OK, what should I do? Now, the kernel knows what to do, right? It's either somewhere in physical memory, or it's actually not a valid translation anymore. For whatever reason, this virtual number should not be used anymore. So at that point, the operating system will treat the page table fault, the page fault, as it wishes, right? Not all invalid PTEs would lead to termination of the process, but some of them could, right? So maybe for a certain virtual page, you had it mapped. Maybe you were using some shared memory and you're no longer using it. So at some point it was a valid translation, but no longer it's valid. You are not given that virtual address range anymore. For whatever reason, maybe you allocated heap and then deallocated it. So when you allocated the heap, you got some pages and they had a valid translation. After you deleted them, they were removed from your virtual addresses space. So those translations are no longer valid. So if you access them, you might get page fault and your program could terminate. But some, like this one, if that page has been swapped to physical to the storage, and and you want to access it, then it's going to trap, and then the operating system is going to bring back your page, and you're going to continue running. So that doesn't cause a termination. Okay, so in cases where the operating system is doing paging, it's going to allocate some physical page to you, and then bring and load that page from the permanent storage to your memory, and then set your page table entry to valid, as we discussed. What if we don't have any free memory? So let's say the operating system has searched the entire physical memory. There was no free space to bring your page. So at this point, operating system has to evict some victim page to make a space for you. So we're going to again talk about this. Which pages should operating system choose to evict? But let's say we sort of find that page, that victim page that we want to evict. Now we're going to look at the dirty bit of that page. So the dirty bit of that page means that this page, if that is set to 1, it means that that page has been updated. So in that case, we cannot just throw it away. We have to go and write it back to the permanent storage, because if you remember, the memory is going to be a write back cache. So if that write dirty bit is 0, we can just throw it away. We don't need to do anything because we have a copy of it in the permanent storage, right? Presumably. So we don't need to write it back to physical memory, to permanent storage if the dirty bit is 0. Okay? Excuse me, I had headache and I had to have coffee to operate for today's lecture for ECE and SE. So apologies for that. Okay, so and if you find some page to evict, then you have to go and shoot down their TLB, for example. If you remember, you have to invalidate all the TLBs, all the translations of this page, because the translation is no longer valid because you're evicting it. You also have to go to the page table entry of the victim and make the valid bit to 0, indicating that this page is no longer valid. Now, bringing a page from permanent storage to physical memory is going to take time. During that time, you could start running another application. So that could happen in the background. So you could DMA, for example, your SSD could DMA the page to physical memory. And while that's happening, you can start running someone else. Once that's done, your SSD will raise an interrupt saying that the page has been copied. Now operating system wakes up and does the rest. So it then sets all the page table entries and stuff, and then potentially context switches. I mean, at that point, you want to make the thread that requested this page to ready, because you have to block it while the page is brought back from permanent storage. And once that's all done, then you can make it ready to be executed. Here is all the things that I just said in figures and in animations. So let's say that you access virtual, your processor, your CPU executes an instruction that creates a virtual address. You go to your PTE, you find your physical page number, you get your offset, and you find the byte that you want in physical memory. Now, let's say next time you do, you get an invalid page table entry. At that point, a page fault exception happens. Now, the page fault handler is going to run. It's going to recognize that there is a page, for example, in the disk corresponding to this page, and we want to bring it back. So at this point, you're going to talk to the driver, the disk driver, to do this for you, right? So once the file is brought back, you're going to update the page table entry, right? And then you're going to make that guy ready for execution. You're going to, if you remember about what we discussed about precise exceptions, if an instruction causes an exception, we're going to re-execute it once the exception is handled with this, which is this case. So you re-execute this virtual address, and now you have a correct translation. You can just continue your execution. Okay. Now let's look at it in another example. So that was for any page. Now let's look at the loading of the executable image. Like the first time, for example, that you want to start executing your code. If you remember, you compile your code, you create this executable image. So where is that? It's somewhere in your permanent storage, right? It's still not in the memory. And then at the loading time, you're going to load it to your physical memory. So let's see what happens in that case. So let's say you have this executable image somewhere in your disk. It has your code, it has your data, maybe some metadata information. Now, the loader, which is part of the operating system, will load the executable image into physical memory, and then sets up all the registers. Maybe like we want to initialize them all to 0. Initialize the stack pointer. So maybe we want to give a stack to this process. You know, a stack is not here at this point, right? When you have the executable image. When you start executing, then you want to allocate the stack. Okay, so we do that. Once we do that, once it's in memory, we can just set up the virtual address space, right? We can have the where this mapping is happening, right? So you also set up your page table to see where each virtual address is mapped to physical memory, right? Now, so yeah, okay. So now let's start that. Let's assume that everything is initiated. Usually in systems, in operating systems, you want to once the system is set up, have a backup of all the pages that you have already in your disk, right? So if you remember, I said if the page that you want to evict is not dirty, you can just throw it away without doing anything, because the assumption is that you have a copy of this page in your disk. So here is that copy, right? So we're assuming that a copy of all the pages that I have is also contained in my disk. So the disk has a copy of every page that my application needs. So this is called the backing store, or the swap files. Okay, and then you set up your page table. Now, in your page table, you have pointers to all the pages that reside in your memory, and every page that is not residing in your memory, you might have a pointer to those. Now, I have to say something here. Now, this pointer, where is this pointer? Where do we keep pointers to the pages that are not in physical memory? Now, page table has a well-defined a structure, right? You have these page table entries. They have this physical page number, right? Now, some operating systems on some architectures use the page table entry. If you remember, there were software bits and there were reserved bits. So these are the bits that the hardware is not using. So you could potentially use these bits to store a pointer to disk. So you could potentially just use the page table entry data structure to have this pointer to where the page lives in the disk. Now, you don't necessarily need to do that. You could also have these pointers inside operating system data structures. So the operating system could have its own software-defined data structures that it stores where each page resides in physical memory. Sorry, in the permanent storage. I got a question. So if we evict a page and sometime later we need to access data in that page, the operating system will have to pull the exact same page from main memory, right? If so, where is that mapping stored of which pages we have used? Okay, so the question might be answered with this example. If it doesn't get answered, please re-ask it. I'm thinking that your question will be answered in this example that we're going to see. Okay, so now that we discussed about that, so we talked about this. So you could potentially use your page table entries to store the pointer to where in the disk this page has a copy or a backup, or you could actually, the operating system can have its own record of where the page resides in permanent storage. Okay, now let's continue. So let's assume that. So another thing to note is that your page table also resides in physical memory. So don't forget about that. So your page tables are also going to be in physical memory. Now, this is another thing. The page tables could also be a subject of paging. So you could evict a page that contains somebody's page table. Just so you know. So, a page table for one process could have multiple pages, and you could end up evicting some of these pages into your physical memory, into your permanent storage, and then bring them back, right? These are like any other pages. The operating system has to know, of course, which pages are evicted, which pages are residing in physical memory. But that's another thing to know. So where is page table? It's basically in physical memory. So some of the pages in physical memory contain page tables. Okay, now let's assume that there is another process. So this was for process 1, P1. Now let's say there is another process 2 here. And let's say this process, so let's say we access a page that has an invalid address. So let's assume that the P1 wanted a data here, a page here that was invalid. So what should we do? Well, first of all, we're going to context switch because we're no longer able to run this guy, right? So we're going to go and start running someone else. But then in the background, we're going to bring this page from, so this is the page in disk. We're going to now bring that page in memory. So in the background, we're going to start doing this translation, right? So once this copying of data could happen by the DMA from your SSD or any other means, we're going to bring the page. So let's assume now that the page that P1 wanted has been brought to memory. So at this point, an interrupt happens, and then the interrupt handler will just set this pointer. So this is the pointer. Now that I have the page in physical memory, I can make this translation valid and make it point to that page. So, you know, either at that point or later on, I context switch. So I start running my P1 again. Now that I have the page, now where do I start? I start with the same instruction that wanted to access this virtual page that had an invalid translation. Okay, so I have two questions here. Are kernel pages subject to paging? Usually not. So we'll talk about this. So you could tell operating system that you're not supposed to throw away my page. So there are ways for a process to tell operating system that you're not supposed to page my apply demand paging to my pages. An operating system can do that for its own pages. So it can make sure that its own pages are not ever evicted. Okay, so another question. If the page table must map the entire virtual address space, wouldn't even large hard drive not be enough to? Okay, so this question is a little bit worrisome. Somebody is asking what, like, a page table would be so big. Well, this was the discussion we had when we were talking about virtual to physical address translation. The original flat page table was so big, but then we started talking about multi-level page table, and then in the process we said that when you have this tree representation, then if you're not using a range of virtual addresses, you don't need to store them anywhere in your physical memory. That way, the size of your page table will be, you know, roughly speaking, the same as the number of virtual pages that you're using. So you don't need to store any data for the pages that you're not using. So with the flat page table, meaning that one page table that contains all the virtual to physical addresses, then yes, the size of this guy is going to be super big. But then we said this is not a good way, so we talked about this multi-level paging, where, you know, if one entry here is empty, then you're saving all the data for this, so you're not storing anything. If you missed that lecture, go back and watch that. So I've answered that question. So basically the end of that discussion is the page table is usually as big as the number of virtual pages that your process is using. So, and then as we discussed at the beginning of this lecture, usually our processes are not using a lot of virtual pages, right? So the size of page table is usually small. Okay, another question. So each page table entry needs to store the position of the page in both memory and disk. I'm a bit confused on how the operating system finds a page in disk based on an invalid page table in memory. Okay, so going back, I didn't say that that's always true. I said you could use page table entry to do that, right? So page table entry is a data structure in physical memory that is used by both hardware, primarily used by hardware and set by the operating system. So operating system goes and sets a page table for the hardware to use it, because hardware is going to traverse your page tables. We discussed that, right? So once the page table is populated by the data from operating system, then hardware can just walk through page table. So that's that. Now, the operating system has to have its own data structures to know the mapping, right? Where to map. So once, you know, the operating system makes a decision and then populates page table. So for that, operating system has to have its own data structures to know where each virtual page is mapped to the physical page. Now, ideally, operating system could just use the page table instead of having two separate data structures, but it's up to the operating system. It's design specific. You always almost all the for everything, the operating system has its own variables and data structures to know where things are. Now, what I suggested was for example, 64-bit page tables or page table entries, you have some number of bits that are not used by hardware. So operating system could utilize those bits to store address for the pages that it puts in disk. So that's one option. Another option is for operating system to have its own, address space, like its own data structure for virtual to physical address translation. Operating system can do whatever it wants in software, right? In software, you can define a linked list or a tree or whatever data structure, dictionary for virtual to physical page translation, right? And then if you get a page fault, then you can go to your dictionary and find a mapping and then come back and set page table. The point being, this page table is a data structure that hardware knows how to use, and it's completed by operating system. So operating system has to know how to work with this page table. But this doesn't mean that operating system cannot have its own data structures. I think I'm hammering the point so much, but so I'm going to stop there. So hopefully I answered that question. I think the question was about swap space. Only the used virtual page are backed. I do not understand this question. Yeah, I mean, that's what I was saying. So only the pages that you're using, you back them up in the disk. You don't back up all your virtual address space. You only back up the virtual pages that your application is using, obviously, like as you can see here, right? So I have only pages that my application is using. All the pages here in virtual address space that are not being used, why should I have them in the disk, right? Okay. Okay, now, what is the cost of demand paging? The cost of demand paging is huge. Like any other cache, we can use the formula we saw for access time. So access time equals average access time equals heat time plus miss ratio times miss time. Now, here is an example. Let's say that average access time to memory is 200 nanoseconds. And let's assume that average page fault service time is 8 milliseconds. So if you get a page fault, it takes 8 milliseconds to resolve it. If you don't and your data is in memory, then it only takes 200 nanoseconds to access your data. Now, let's assume that the miss ratio is P. So basically, this means that 1 minus P, I'm going to hit in memory, with probability P, I'm going to miss in memory. So then I'm always checking memory. So this is my hit time. I'm always paying that cost, 200 nanoseconds. Plus, this is the miss ratio, P, times, if I have a miss ratio, then I'm going to spend 8 microseconds to resolve that page fault. Now this gives me a 200 nanosecond plus p times, now 8 microsecond is 8 million nanoseconds. So we're comparing 200 nanoseconds to 8 million nanoseconds. Now let's put different p's for this and see what this average would be. If 1 out of 1,000 accesses to memory results in a page fault, then this is micro. So then estimated average access time would be 8.2 microsecond. Now this is 80 times more than your usual access to memory that hits. If you want, so this is huge, a slowdown, right? So if 1 out of 1,000 accesses you miss, then your average access time is going to be 40x more than the ones that hit in memory. Now, what should P be for this slowdown to be negligible, for it to be 1.1x? So if we want to get to 1.1x, what should P be? And if you do the math, then P should be this number. Then P, the probability of missing in memory, should be less than 2.5 times 10 to minus 6, which basically means something like this. You have to have one page fault every 400,000 accesses. So the whole example here is there to show you that a single page fault could screw your program so greatly. So as much as possible, we should avoid having page faults. We should avoid demand paging, because if you end up demand paging, if you end up having an invalid page and then you have to bring it back from memory, it's going to screw up your program. And if that's going to happen, you have to make that probability so low, right? Okay. Now, again, like any other cache, what are the factors to have misses in memory? The first is compulsory misses. These, if you remember from caches, these are the misses where this is the first time you're accessing the data. So usually there is not much we can do. The only thing that you could potentially do is to prefetch. Prefetching means that you're gonna predict somehow that a certain page is going to be accessed and then bring that page to your physical memory beforehand. Now you have to be careful because prediction is prediction and it has a prediction error. So if you make a mistake in your prediction, you might populate your physical memory with unwanted pages, and doing so means that you're having less memory for wanted pages, which would then increase the probability of you having capacity misses, because now the usable capacity of your memory has decreased because you're using your memory to cache unwanted pages. So for the wanted pages, now the memory is smaller, as if. Okay, so prefetching is good, but if your prediction accuracy is really high, knowing what pages you want. This is an area of active research, at least in computer architecture. So getting some virtual addresses and then guessing what other virtual addresses or physical addresses are going to be used in future. Capacity miss basically is what I said. So if you don't have a space, well, you will end up having capacity miss. Now, to solve this, you have to have bigger cache. And in the case of memory, you have to have bigger memory. So one option is to increase the amount of DRAM. Another option is to so the other option that you have is to make sure that the capacity is allocated to different processes appropriately, right? So for example, if your allocation policy is to divide memory equally between all your processes, let's say you have four processes running, and you have 4 GB of memory, you might decide that I give 1 GB to each process. Now, this is kind of might be fair, but what if one of the processes is not using any of physical memory? Maybe it's using like few megabytes, but then another process is using 2 GB. So the one process that needs 2 GB is going to start thrashing itself, because within that 1 GB, it cannot fit all the data it needs. So it's going to start demand paging its own pages. Whereas the page that is given 1 GB, sorry, the process that is given 1 GB and only needs few megabyte is not going to use its memory. So, you know, if you really want to avoid paging, then you might actually want to allocate physical memory based on the need of application. But then when you go and do based on need, you then have to be careful about fairness. So there's always a trade-off between fairness and performance, as we saw it in CPU scheduling. The same stuff happens here in memory allocation. I got a question here. So it says, how does the operating system prevent compulsory misses on system startup? Yeah, I mean, sometimes those are unavoidable, right? Now, if you remember, we talked about the boot up of your system, and one of the first things that happen is that your bootloader is going to bring the kernel image to memory. So hopefully you bring everything necessary so that you don't get demand paging at startup or boot up of your system. But then when you start running applications, sometimes it's unavoidable, right? And then you have conflict misses. Conflict misses happen when you have sets and set associativity. Because we have fully associative cache here, then we're not going to have any conflict miss. So everything is going to be a capacity miss. And then we will have policy misses. So policy misses are misses that happen because of bad eviction policy. So let's say that you looked at your memory, you didn't have a space, and you wanted to pick a victim and bring another page. If you pick the victim unwisely, let's say you pick a really popular page, a page that is accessed again and again and again. Maybe it's a clib library that is accessed by every program, and you pick that page to evict. Then that was a bad decision, because it's going to end up resulting in a lot of misses. So that's a policy miss. So you picked a wrong page for eviction. Let's say there were other pages in your memory that nobody was using, and you could have evicted those, but then you wrongly picked a popular page, and now that is ending up producing a lot of misses. So that's a policy miss. Okay. So that's a good segue to start talking about replacement policies. So when we were talking about caches, the first one that we talked about was random eviction. So if you need to evict someone, randomly pick someone and throw them away. Now this is simple, but it's absolutely not efficient. What if the randomly selected victim is a popular page? So it has really bad performance implications. And it could cause, like, maybe you pick a good page, maybe you pick a bad page, and depending on this randomness, you can actually end up having really unpredictable performance. The other one is first come first serve, so, or first in first out. You could look at when you brought pages and then throw out the first page that was brought to memory. This way, you're kind of making sure that every page gets a fair share of time staying in memory, right? Because the first page that was brought to memory has been there for a while, so I'm going to throw it away now. Now, this is kind of fair, but again, what if that page that you brought first is a popular page? Maybe it's like a clib library page and everybody is using it. So if you evict it, you're basically harming everyone. So it's not optimal, right? The decision based on when we brought the page is not a good decision. Now, what is optimal? If we really want to pick the best page to be evicted, what would that page be? So this is what minimum would do. Minimum is a policy that picks the page that will be accessed the longest in the future. So let's assume that I know future. I know all the accesses in the future. If I know that, then I'm going to see which page will be accessed the furthest in the future. So this is a page that is not going to be used for a while, and then in long term in the future it's going to be accessed. So this page is the page that I have to evict. So this is optimal. You can actually prove it that this is the best you can do. If you evict any other page, your performance degrades. So you could, instead of doing that, evict this page that is going to be accessed furthest in the future and prove that your access time goes down. Now, this is impractical, however, because who knows future, right? At any given time, I don't know what accesses in the future I'm going to be having. So this is kind of like a benchmark to compare against. Like if I have a trace of memory accesses, then I can say what would have minimum done for this trace, right? If I have all the things that are going to happen in the future, then I can process it and then say what would have been the best replacement policy. So that would be the minimum. But during the execution, I don't have it. So it's impractical. It can just be used as a benchmark to compare other policies. Now, an approximation of min is called LRU. You probably have heard LRU policy. It's called least recently used. So the idea is I don't have information about future, but I do have information about past. I know all the accesses that have been done and have been made in the past. So I can pick the access that was done the least, basically the furthest in the past. So that is a page that I haven't been using for a while. And the intuition is if there is a page that I haven't been using for a while, I'm probably not going to use it in the future as well. So that's the idea. So if I don't have an idea, if I don't have information about the future, I can use the information about past. Now this looks like LRU. Sorry, this looks like mean, but it's not exactly mean. So it's not optimal, but it's a good approximation of mean. It makes sense. Now, the downside of this is that it's very, very difficult to implement this because it requires us to track all the accesses, right? Because we want to find a page that was accessed the furthest in the past. This means that I have to track all the accesses. Now, can I do that really realistically? Unfortunately not. Because if you remember, most of our accesses are handled by the hardware. So hardware is not going to bother us. Hardware is going to go to TLB, go to page table entry, and then access the page. Hardware is not going to wake us up for every page access, because otherwise we have to wake up on every instruction, because then every instruction accesses memory. And we've already discussed that waking up operating system on every access is too much. So we need to track all accesses to implement LRU precisely. And it's not practical to do so. So we're going to talk about approximation of LRU. So we're talking about two levels of approximation. The first one is we're going to use LRU as an approximation for mean. And then we're going to approximate LRU because we don't have access to all the information about all the accesses in the past. So talking about approximate LRU comes next. Let me answer the question that was asked here. Why is the random eviction a typical solution for TLB? Wouldn't this cause potentially expensive page table walks if we just evicted translations randomly? The thing about TLB is that TLB is very, very small. So if you remember, TLB only fits 256 in some cases. 256 entries you have in TLB, right? Now, if you want to do some crazy algorithm, you want to implement some crazy algorithm for your TLB eviction, what will happen is that you're going to make your TLB slower, because the more logic you put in your TLB, the slower your TLB becomes. Now, you have to pick, because you're going to pay the TLB access time for every instruction. So making TLB smarter for eviction comes with a cost of making TLB slower. And you probably don't want to pay that cost. That's why you might actually end up randomly selecting one of them. Now, of course, randomly selecting which one to evict has a cost, right? Because then you have to go and do a TLB. But, you know, again, implementing an exact one might not be beneficial given the cost of doing it for TLB. So you have to be really careful with TLB. We want TLB to be as fast as possible, as less hardware should go to TLB as possible to make it as fast as possible. And you know, implementing any smart eviction policy means more hardware. And you have to, again, keep in mind that TLB is very small, so you don't have many options to choose from. You have only few options, and you know, almost any one of them you choose, you're going to pay a price, because you know, there is a chance that you're going to come back to that translation, and you're going to need that translation. So it's kind of like you're going to choose where to pay a cost, and probably not a good pick for TLB. Okay. Now let's look at FIFO. So here is an example. Let's say these are your references. So you're going to access A, B, C, A, B, D, A, D, B, and then CB. So initially, let's assume that your memory has only 3 pages. Initially, your memory is free, so you're going to cache A, cache B, cache C. So at this point, your memory is full. Now A comes. It's in memory, so it will be a heat. B comes heat. Now D comes. We don't have D, so we have to evict someone. Who are we going to evict? We're going to evict A, because it was the first one who was brought to memory. So D is going to come for A. Then A is going to come back which one am I going to evict? B has been there for a while, so I'm going to evict B. Now D comes, D hits. Now B comes, B is going to kick out C. C comes, C is going to kick out D. B comes, B is going to hit. So this is just an example of 5 fault. So we had 7 page faults. 1, 2, 3, 4, 5, 6, 7. So did I say 6? 7. 7 page faults. Now, this probably was a bad call, right? Because immediately after we kicked A out, we had an A access. So if we could have looked at future, we would have kicked C, right? Because A is accessed here, B is accessed here. C was the one that was accessed the furthest in the future. So we could have kicked out C and put D here, and then A would have hit here, D would have hit here, B would have hit here, and then eventually we would have brought D. So we would have had less cache, less memory, less page faults. Now, actually, let's look at mean. How mean does this? The same. So A, B, C, A, B. Now, instead of D, we're going to kick, as I just described, we're going to kick C out. A is going to hit, D is going to hit, B is going to hit. Now, C is going to come. I don't have the future to show you, but at least we know that B is going to be accessed. So I'm not going to kick B out. So I'm going to choose between A and D. I'm choosing A, assuming that A has not appeared in the future. So now how many page faults? 1, 2, 3, 4, 5. So with mean, I got 5 page faults. Now let's look at LRU for the same example. A, B, C, these are okay. Now D is gonna come. I'm going to kick out the one that was accessed the furthest in the past. So which one? A is the one that was accessed the furthest in the past. So I'm gonna kick A out. Now A comes between D, B, and C. Which one should I kick out? The one that was accessed the furthest in the past. That's B. So I'm gonna pick B. Now B comes. I have between D, A, and C. Which one was accessed the furthest in the past? Well, it was C. So I'm going to kick C out. But then, unfortunately, in the next is C. So which one should I kick out? Now B was accessed here. A was accessed here. D was accessed here. So D is the one that was accessed the furthest. So I'm going to kick D out. Unfortunately, the next one is D. So now, between C, A, and B, A is going to be kicked out. A comes, kicks out B, so on and so forth. So in this one, I'm paying a page fault. I'm incurring a page fault on every access. So LRU in this particular example is worse than everyone. So it's even worse than first come, first serve. That's why I said LRU is not exactly mean. The intuition is that if a page has been accessed the furthest in the past, you're not going to access it in the future, but that is not always the case, as you can see in this example. So in this example, the page that was accessed in the past is actually the page that is going to be accessed next time, all the time. So this particular example is the worst case scenario for LRU. You know, mean does a lot better for this particular example. So I'm not going to run mean, but mean is going to do 1, 2, 3, 4, 5, 6. So 6 page faults for mean. Well, as LRU had how many page faults? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 page faults for LRU, whereas mean only has 6 page faults, so twice as many. Okay, so we're kind of done with the discussion about demand paging. So what is left? Let me look at the remaining slides. Okay, so as I said, this LRU example that we saw is very expensive to implement. Now, we're going to try to, so the next topic that we're going to see is how to approximate LRU. So, but before doing that, let's talk about something that that is interesting now that we've compared these different algorithms. There is this Blady's anomaly that is very interesting. So usually you expect your page faults to go down if I give you more memory, right? Because giving you more capacity is going to potentially decrease your capacity misses, and you're going to have less page faults. Now, turns out that this depends on the policy that you're using for your eviction. Now, here is the anomaly. So in this example, I'm using, this is for FIFO, so first come, first serve. This is the example that we saw. So D here kicks out A here kicks out B here kicks out C, and E and C and D. So in this example, you have 9 page faults. Now let's increase the memory. Let's increase the memory to have 4 pages. So in this example, the first one, my memory had 3 pages. Now let's increase it to 4 pages and look at the same trace and see how FIFO does. So all the 4 first ones are going to miss. Then A and B are going to hit. E is going to kick out A is going to kick out B is going to kick out C is going to kick out D is going to kick out A, E is going to kick out B. How many page faults? Well, it's 10 page faults. So I increased my memory, but that increased my page faults. So that's very counterintuitive. So this happens because of the way FIFO works. So by increasing the memory, I'm aligning the accesses. So I'm getting these 4 page faults. Now, it's not the case. So if you actually implement LRU or mean, increasing the number of pages would decrease your page faults. But for FIFO, for example, that's not the case. So if your replacement policy is FIFO, there are cases where you increase the capacity of your memory, and that increases your page faults, that's why it's an anomaly. Okay, now let's go back and talk about LRU implementation. How can we implement LRU? So let's say if in ideal world we had access to the information of which pages have been accessed in the past, then I can just have something like this. So some notion of like a list of pages that have been accessed. So every time I access a page, I bring it to the head of the queue. And every time I want to evict, I will evict the last page in my list, right? So this would be a potential implementation. But this works if I get notified every time a page is accessed. Every time a page is accessed, I'm going to bring it to the top of the list. But unfortunately, you know, getting this information is not possible because hardware is not going to wake operating system up every time a page is accessed. Okay, so what should we do? How can we deal with this? Now, this is where that access bit comes handy. The access bit that we talked about, this is where it comes handy. Now, we're going to talk about this clock algorithm in details next lecture, but just to set up because clock algorithm also has some, you know, additions and extensions, but the main idea is, let's say I'm looking at this access bit of my page. So each page in page table entry has an access bit, which is set by hardware. So hardware, every time it accesses a page, it sets that access bit to 1, indicating that this page has been accessed. Now, one thing you have to remember is it does it once when it looks up the address translation in the page table. Once this is cached in TLB, further accesses in TLB, they don't go to page table. So we're not going to set this many times. It's just a 1 and 0 bit. So we might have set it once to 1, and then we might have accessed it again and again and again in TLB, or we might have accessed it once and never gone to it again. So both scenarios could happen. That's why this is an approximation, because we're going to say that this page was accessed, but the operating system doesn't know how frequently. It just knows that it was once accessed. Now, clock algorithm kind of has this this clock hand. So we're going to put all the physical pages around the circle. I don't exactly know why I did that. So now I got all the information. Yeah. Okay. So now the hand is pointing to a page. If we get a page fault, this wherever the hand is pointing to is going to be the victim. So what's going to happen is, I guess not that one. I always yeah, it's so we're going to advance the hand, and then the next one is our victim, not the one that the hand is looking now, the next one. So let's say hand is looking at this guy, and then let's say we have a page fault. At this point, we will advance the hand. Now hand is pointing to this one. Now we look at the access bit of this one. If the access bit is set to 1, this means that this page was accessed. So we're going to not evict this guy. So we're going to advance the hand another one and check the next one. Well, this one also has an access bit of 1. So I'm going to advance one more, check it. It also has a 1. So eventually I'm going to get to this guy, which has an access bit of 0. This means that this guy hasn't been accessed. So this becomes my victim. So I'm going to evict this guy. Now, while the hand is advancing, the operating system is going to set the access bit to 0, because now I checked it and it was 1. So I'm going to set it to 0. So that next time I come over, I have a clean slate. Now, this is not enough, because this is done in page table entry. We know that the TLB this page table entry could be in TLB. So operating system also has to shoot down whatever is in the TLB. So that the next time that the hardware tries to access this, then it has to come to page table entry and set this bit to 1 for us. So that's that. That's pretty much what it does. So as you can see, this is not exactly LRU, because we're not looking at the page that was accessed the furthest in the past. We're just finding one page that was not accessed from the last time we visited that page. Now, again, it's kind of like grouping pages into 2 sets, a set that has been accessed from the previous time until now, and pages that haven't been accessed from the last time until now. And then we're going to pick the first one among those haven't been accessed that is close to the hand of the clock. So that's pretty much the high level algorithm here. Now we will extend this, we'll make it more sophisticated, but the vanilla clock algorithm is what I just described to you. Okay, I got a question and then never mind afterwards. So I assume that the question was answered. Okay, so thank you for sticking around, and we'll talk to you on Thursday. Take care, be safe. Bye.